Welcome to this explainer. If you've ever stared down a messy algebraic equation packed with square and cube roots and felt that familiar sense of panic, well, you're in exactly the right place. Today, we're going to break down the sometimes intimidating world of radicals and transform it into a perfectly logical puzzle. Think of this session as your ultimate toolkit for mastering algebra. By the time we wrap up, you won't just be memorizing rules, you're actually going to understand the hidden machinery behind them. All right, here's our roadmap for mastering radicals today. We're going to hit 1. The core root laws, 2. Anatomy of a root, 3. Prime factorization technique, 4. Beware the addition trap, 5. Combining and simplifying radicals, and finally, 6. Multiplying radical expressions. Let's get to it. Section 1. The core root laws. Let's dive right into our toolkit and check out the rules for multiplication and division. What's super cool here is how beautifully this pattern just repeats. First up, square roots, and then right next to them, cube roots. If you've got the square root of a times b, you can literally just split that right up into the square root of a times the square root of b. And you know what? The exact same logic applies to division, and yes, the exact same logic applies to cube roots too. It's this awesome universal rule that lets us take big, clunky problems and break them into bite-sized, manageable pieces. Moving on to Section 2, Anatomy of a Root. Now, before we start tackling complex equations, let's just hit pause for a second. We gotta make sure we're speaking the exact same mathematical language here. Basically, every radical expression has two distinct living quarters. That number tucked safely inside the radical symbol, like the 2 we have here, that's called the radicand. Meanwhile, the multiplier hanging out on the outside, the 3, is our root coefficient. Nailing these two terms down is absolutely crucial because throughout this whole explainer, we're going to be shifting numbers from the radicand position out to the coefficient position, and vice versa. Section 3, Prime Factorization Technique. Okay, so moving numbers around sounds great and all, but how do we actually do it? Well, here is the absolute best blueprint for simplifying a massive, messy radicand, the prime factorization technique. Whenever you're facing down a huge number inside a root, just lean on these 3 reliable steps to systematically crush it. First, divide the radicand by its smallest prime factors. Think 2, 3, or 5. Second, take a look at those factors and start grouping them. If it's a square root, group them into pairs. Cube root, look for triplets. And finally, step 3, take those grouped factors and move them right outside the root as a single root coefficient. Easy as that. This perfectly shows the latter method in action. Just look at the number 18. We divide by 2 to get 9, then divide by 3 to get 3, and divide by 3 once more to get 1. So our prime factors are 2, 3, and 3. Now, since we're dealing with a square root here, we just circle that pair of 3s and pull them out as our brand new root coefficient. And that lone 2, the one without a partner? Well, sadly, it's staying home tonight, tucked safely inside as our new simplified radicand. So the square root of 18 elegantly transforms into 3 root 2. It seriously takes all the guesswork out of the equation. All right, Section 4, Beware the addition trap. Okay, listen up because I need you to pay close attention to this next part. We are about to bust the single most common math myth that catches students off guard all the time. Check out this warning. The square root of a plus b does not equal the square root of a plus the square root of b. I repeat, it does not. While multiplication and division play super nicely with roots, addition and subtraction absolutely do not. You just cannot split addition or subtraction across separate roots. No way. Let's actually prove this so it sticks with you forever. Adding root 2 and root 4 does not magically equal root 6. If we actually run the numbers, the square root of 4 is 2, and the square root of 2 is, well, about 1.414. So that left side gives us roughly 3.414. But the square root of 6, that's only about 2.449. See? Not the same. And that is exactly why we have to simplify each term individually first before we ever try to combine them. Don't fall for the addition trap. Moving right along to Section 5, Combining and Simplifying Radicals. So, if we can't just mash numbers together with addition, what's the game plan for those massive equations that have multiple radical terms? Well, before we combine them, we need to know how to move things in the opposite direction. We already know how to pull numbers out using that prime factorization ladder, but sometimes, to solve a puzzle, you gotta move a coefficient back inside the radical. To do this, you literally just reverse the rule. For a square root, you square that outside number as you push it in. So an a on the outside becomes a squared on the inside. For a cube root, you cube it. To put that into perspective, if you've got a 3 on the outside of a square root and you pop it back inside, it turns into a 9. This kind of flexibility is an absolute game changer for simplifying complex fractions. Let's walk through this masterpiece of a problem together. At first glance, root 45 minus 2 root 20 plus 2 root 5 looks, frankly, impossible to combine, right? The radicands are all completely different. But hey, remember our toolkit. If we break down that 45 into 9 times 5 and pull out the square root of 9, it becomes 3 root 5. Then we break down the 20 into 4 times 5, pull out the square root of 4, which is 2, multiply that by our existing outside coefficient, and boom, we get 4 root 5. And would you look at that, we just revealed that every single term actually shares a common radicand of 5. Now it's just basic arithmetic on the outside. 3 minus 4 plus 2 leaves us with 1. Beautifully simple, root 5. Finally, section 6, multiplying radical expressions. All right, we've totally mastered single terms, so let's level up to binomials. Our final tool handles distributing terms with roots exactly the way we would with standard algebraic variables. So the key here is applying those core multiplication laws we talked about earlier. We distribute the 2 root 3 to both terms inside the parentheses. First up, 2 root 3 times root 6 gives us 2 root 18. Then 2 root 3 times 5 gives us 10 root 3. But hold on, we aren't quite done yet. We always check to see if we can simplify further. So we run our trusty prime factorization ladder on that root 18, pull out a 3, multiply it by the 2 sitting on the outside, and we arrive at our final elegant answer of 6 root 2 plus 10 root 3. Now I've got a fantastic pro tip for you that'll make you feel like an absolute math wizard. If you're multiplying two complex binomials and you spot the classic difference of squares pattern, where the terms are identical, but one is addition and the other is subtraction, like a plus b times a minus b, you are in luck. You don't even have to FOIL out the whole thing. You can literally just square both terms and drop the radicals altogether, because those messy middle terms naturally cancel each other right out. It just boils down to a squared minus b squared. Seriously, keeping an eye out for this pattern will save you so much precious time. So, having built up this incredibly sturdy toolkit for square and cube roots today, you really have to wonder, what other seemingly impossible algebra problems are now just waiting to be broken down by your new foundational skills? Think about it. You now know how to look right past the surface of complex numbers and spot those prime factors hiding inside. You know exactly how to manipulate both the radicands and the coefficient. These laws of radicals, they aren't some big mystery anymore. They're your strategic advantage. So, if prime factorization can crack the code of any complex root, what other massive, intimidating problems in math, or even in life, are just waiting for you to come along and break them down into their smallest, most basic prime pieces? Thanks so much for joining me on this explainer, and keep hunting for those invisible patterns.